Let's pull the box across the floor. So let me draw a picture so we can clearly see what we're talking about. It's very similar to what I drew on the last video. So I'm pulling, I mean, this could be like your suitcase behind you, if you will. This is my applied force, and I'm told that this angle here is 37 degrees. And my displacement is going to be that away. Let's see, 100 newtons. Oh, 40 meters. I was looking for the distance. It's like, huh, I didn't give you everything you need. So we're going to do this all for 40 meters. Now, unlike how we began everything, there is this friction force that's going to resist this motion. So I have two things that are doing work on this box. One is me pulling it, making it go, and this friction force is doing work. It's taking energy out. So I'm not going to get the full amount of energy into the box just from my pull, because some of it is being lost to friction. That's all that says. So this one, though, let's just break it down into the pieces. And we're going to get to where we're going to create just like one general equation from this. And I can go, so then work, let's go friction first. Work from friction. Remind ourselves that the general equation for work is that work equals FD cosine of theta, where theta is the smallest angle between them. So if I'm looking at this friction force between this box and the floor, what is the angle between the displacement vector and the friction force? Hopefully you see that it's 0. They're both in the exact same, I'm sorry, this one would be 180. Oh, did friction first. My direct displacement is this way, and my friction is this way. So my friction is resisting the motion. So my theta for friction is 180. Let's see, and we know our displacement is this 40, and we know that friction exerts this 50 newtons of force. So I can put this into my work then. Let's just go work from friction is, let's see, force of 50 newtons times 40 meters times the smallest angle between them, cosine of 180. We've been doing a lot of things in radians, so when you put these things in your calculator, make for darn sure that when you're given something in degrees, that you're answering in degrees. Okay. So what this piece does is makes this sign negative. So I'm going to get this negative 20, 2000 Newton meters, otherwise known as negative 2000 joules. Cool. Now, what about the force that I'm applying? The work that I'm getting out of my applied force. So work applied. Okay, so now this is in the direction of my displacement. Same thing. So this is going to be just 37 degrees. So my theta there is 37. And then I can rewrite this as then my work applied is going to be the force, this 100 newtons, times the displacement, this 40 meters, times cosine of 37. So that gives me that the work from that applied force is 3195 Newton meters, or 3195 joules. So now here's the fun thing. The next question, yeah, it does ask for net work done. So we've answered these pieces. That's the work done. The net work, not like TV, it's the net amount of work, is going to be the sum of all of my works. So my work applied plus my work from friction. But here I know I have my work applied is the 3195, and this one was negative, so minus 2,000. So that gives me 1,195 joules, and it's a positive value. This is bigger than that. So that's the net work done. Now, can we figure out, we weren't asked that, but we could figure out, couldn't we? Let's see, we don't know what the mass of this thing is. I know the energy that it has. I know that the force from friction is this 50 newtons. That'd be kind of fun. Because I could go force, gravity. Oh, I could turn that into a fun question and relate this back to the force of friction and our previous problems that we've been working on. That would be fun. Try that one and let me know. See if we can't figure out what the mass is. Oh, I hate that when I don't read what the question is and the information I wrote down. So you can see what the mass is. So from that, we could figure out what the coefficient of friction is. Figure that one out. There we go.